Our next speaker is Paul Millar. ESFRI communities. So Paul, please.
So, can you hear me okay? And
yes.
hopefully you can see my slides okay.
Yep.
Good. Start video. Sure. Is that working? No, it doesn't seem to be. Okay, well, I'll just stay invisible, and you've got my slides there. Good. Okay, so my thanks to the speaker organizers for this opportunity to speak. This is a little outside my comfort zone for talking about HDF5. I've hinted at that earlier. My kind of day job is as one of the senior developers in a open source software project. It's developing storage software for scientific data, but I sort of increasingly take on a sort of a consultancy role, helping various science communities, research communities in data management, architecture design, this kind of thing. And through that, I'm involved with an EU project called ESCAPE, which is, I'll give you a quick, relatively quick introduction to that, so you kind of appreciate what it's trying to do and why it might be interesting. So here are some rather boring facts about ESCAPE. It's EU funded. It's got quite a large number of partner institutes and organizations. It's a healthy budget. It's been going for kind of 2.5 years now, and it's got a year and a half to go. There's a kind of a picture where you can see the institutes. I really got that there, so you can see DESY as my home institute there, as one of many involved in ESCAPE. So what are we doing? So we're helping scientific research in particular fields primarily. It's predominantly astronomy, actually, and you can see here some selection of these communities here. So there's the spectrum is sort of a selection of areas of the EM spectrum. So we're covering radio astronomy with SKA and VLBI, through to visible light, and then through to gamma rays with CTA. There's a few missed off there as well, but that covers the kind of idea. And then there's sort of the more novel astronomical detectors, if you like. So they've got the gravitational waves detector and neutrino detectors there as well. Sort of in addition to that, so that's the astronomy side, and in addition to that, there's also a sort of a collider research going on. So we've got the Large Hadron Collider, which is in sort of roughly 3 years' time, looking at high luminosity upgrade, which will be quite challenging, to put it mildly. So we're looking at various technologies to help with that. And there's also a nuclear physics facility currently being built here in Germany, which is called FAIR. So that's kind of gives you an idea. There's a fair number of scientific domains that we're kind of looking to help. Many of these are not yet built, not yet running, so it's kind of the ideal time to help with their infrastructure needs. ESCAPE itself doesn't exist in a vacuum. It's part of the EOSC infrastructure, and I'm not going to say too much more about EOSC, but the interesting part here is that ESCAPE itself is split into, it's actually 6 work packages. 5 of them are listed here. So these are sort of different focuses, different of scientific research and scientific the work that people do. The particular one of interest for me, or the one I'm involved with directly, is called DIOS, which is work package 2. This is the data integration for open science work package. And here you can see where there's the logos on the right are the science communities that we're directly involved with in ESCAPE. So DIOS itself is work package 2. This is basically looking at how you manage data, how you store it in a federated environment. So it's with the idea that it can scale up to quite large, what's large, but for what we consider quite large in multi-exabyte capacities, which is kind of where the larger facilities and larger science communities will need to go in the next few years up to that kind of scale. So we're looking for stuff that will work reliably without requiring huge amounts of people, the number of people looking after things. So it should look after itself as much as possible. Is this so we're developing these blueprints for the communities to use in their environment, and these blueprints don't come from a vacuum. We're not starting from scratch. We're actually based on the experiences from the Large Hadron Collider, which has been using federated storage for best part of 20 years now, in a collaboration called WLCG. This is a worldwide collaboration with ballpark figure 100 research institutes and universities spread throughout the world. And these people are providing storage capacity and computing resources for doing analysis. Initially, it was purely for the LHC. Nowadays, it also includes other similar-ish technologies and scientific research, such as Bell 2 and June. These are other experiments and activities, somewhat related. But it's this kind of federation we're using this as a starting point, and we've kind of boiled it down to what we're calling a data lake as a concept. I'm going to talk a little bit more about data lakes in the next slide, but just to finish off in WP2, there's 5 tasks within WP2. So this is 5 things within storage. The first one is kind of the most important one, but this is the kind of nuts and bolts of the data lake concept, including building up a test bed that we're using to really kick the tires and make sure this thing works. There's data lake orchestration service, which is the task I'm leading, which is more high-level stuff. Then there's integration with compute, which is basically testing, being able to test our testbed. Networking, dealing with awkward network connections, and authentication authorization, knowing who you are and what you're allowed to do. So that's sort of the activity within ESCAPE, and with the data lake itself, this idea of federating storage capacity. The key idea is to kind of abstract where data is located, so that as a scientist, you don't need to know, or shouldn't need to know, where data is located. The system itself should take care of that, provided you give it some input about what you want. So that's done in terms of Rusio, this top level component here, which says where data should be and checks where it is. And if it's not where it should be, it tells the next layer down, FTS, to actually copy data around, to possibly even delete data, to satisfy what it believes is the correct location for data. And both these components are a third generation, third time, kind of rewritten 3 times, based on operational experience over 20 years, blah, blah, blah. So they're reasonably well architected, and they're used in production for storing LHC data and elsewhere, in addition. We've also got a caching layer, which which you can deploy instead of a full managed storage endpoint. That could be a lightweight thing that you deploy dynamically, for example, in the cloud, or just as an opportunistic cache. You access data either directly, so literally reading from where the data is stored, perhaps through a cache, or the other sort of popular option is you just download the data that you need locally, something like attached storage on a cloud system, or perhaps even a hard disk on a server, that kind of thing. And then you can access the data or analyze it from there. And the output that you generate, I mean, you don't have to, but quite often you want to then write that back into the data lake as a sort of archival storage to satisfy FAIR criteria, or perhaps for direct reuse. So I mean, you can have a pipeline of various activities, and one triggers the other, and you're using the data lake to store that. So you abstract where the data is. You can then run the analysis in different locations, that kind of thing. So the data lake itself is largely file system, largely file format agnostic. But I was kind of curious where HDF5 is used within the ESFRI communities that are involved with Scape. So I did a little survey. This is kind of not really a definitive answer on these things, but it's kind of at least a kind of holding the seaweed up, get a feel for things. So KM3net neutrino detector. This is they're using HDF5 mostly for publication level data, so stuff that they make public. The underlying format is root rather than that, but it's the public data is there in HDF5, and there's a link there. If you have the slides, there's a link you can click on to take you to further details there. CTA, the Cherenkov telescope array, that's not yet built. They're still figuring out how they want to do data management. They're investigating HDF5, but haven't made a decision yet. But certainly HDF5 is a clear contender in how they want to use, how they want to store data. The MAGIC telescope, this is a precursor or a pathfinder for the CTA, so it actually exists, but they don't use HDF5. The interesting thing here is that the scientists involved in ESCAPE from the MAGIC project are also involved with a bioimaging project in sort of co-located. They're both in Barcelona, PIC. So and they're interested in storing HDF5 bioimaging data into Rusio, which is basically a data. And then you've got basically a data lake, the data lake concept there. So there is interest there, just not so directly. SKA, similar to CTA, it doesn't exist yet. They're still figuring stuff out. So there's no clear decision yet, but HDF5 is a clear contender. They're interested, and they are actually testing it out. The EGO-Virgo, they're using it. This is somewhat similar to KM3net. They're using it for the sort of public data. Their internal low-level data. The less well-processed data is then using custom format. And LOFAR is I mean, that's an experiment that's up and running, or a facility that's up and running. They're using HDF5 quite a bit, from my impression. They've even gone as far as writing a paper on proposing HDF5 as a standard approach for radio astronomy there. So this is the slide where I expose my my ignorance in HDF5. So this is just ideas really to stimulate a discussion and to stimulate questions. So my impression, rightly or wrongly, perhaps wrongly, I don't know, the HDF5 libraries that support HDF5 are largely based on POSIX access, a local file system. And this has, for a kind of a distributed data infrastructure, such as the data lake concept that we're pushing in ESCAPE. This means that, that works, but you need auxiliary mechanisms to download the data set onto the local storage and then process it there. We need to download all of the data you need and process it there. So one of the things that I kind of flag as possibly of interest is remote IO. In HDF5, just as a comparison, in the particle physics community, there's a framework called Root, which has an IO subsystem that's pluggable. You can then access data, not just POSIX, but also remotely. So there's sort of libraries that support this kind of remote IO operations that might be available, might be useful in going down that route. I mean, remote reading, there's some use benefits there. So I mean, if you've got workflows that read only part of your file, if you read only 10% of the file, then you download all of your file that's 90% of the file that you've downloaded and not actually read. Replica discovery, if an endpoint or the storage endpoint is no longer available, you can then seamlessly fail over to another location and get it from there. read ahead, so latency hiding. It's similar to the first one. That normally, you know, when you're reading a file, you want to process the data that you've just read before reading the next one, and we've got some technologies that allow a system to download the data that you don't have. You want to read, ideally, all the data you want to read next, in the background whilst you're processing the data that you're just doing. There's also, I mentioned, there's caching layers there as well, and there's sort of different caching algorithms, and even providing hints to caching layers to suggest, you know, this bit of data or even this file I'm going to read once, don't bother caching it, whereas other ones, yeah, maybe that's of interest. So that's and obviously remote writing. This is kind of, you can either write it locally and then upload it to the data lake, or even write directly. That's more just to kind of keep the scientists' jobs easier, make things easier. The other thing I kind of thought, it's more of a placeholder than anything else, is metadata handling, which is kind of goes a bit towards the query language presentation, the earlier one. If you can push some of your metadata into Russia has the facility to store file level and dataset level metadata. So if we can push some of that metadata in there, then you can maybe do file selection based on metadata stored inside the file, and therefore avoid downloading data only to discover, oh, you know, I've downloaded this data set and turns out that I'm only actually using one file from it. So that potentially interest there. So so anybody who's fallen asleep, this is the point you wake up. This is the conclusion. So ESCAPE is an EU-funded project. It's kind of 2/3 the way through, let's say. Its runtime. The data lake is a key concept there. It's kind of battle hardened over a couple of decades worth of use at CERN, but we're trying to make this available for other communities. Various of those, some of those communities, not all of them, but a good number of them are adopting or investigating HTF5 as a file format. And although DataLake is, to a large extent, file format agnostic, there's the potential here for some collaboration, possibly. So, you know, that's that. Discuss.
So thank you very much. We have probably 1 minute for questions, if there are. And I can comment that there's definitely interest in remote access. We have some experimentation. We now have an HTF5 library mechanism to implement this, but we only experimented with remote reading using ESFRI, using S3 VFD. But there were plans and outline design for read and write VFD. So if there is an interest, we'll be happy to talk about it. We kind of know how to do it.
I also might want to add that there may be some interest, there may be some possibilities with the highly scalable data service that John Reedy will talk about. So yeah, that last slide really raised a lot of really interesting issues that some work is being done on. So great.
Yeah. Thank you. So let's, once again, please use chat window if you have questions.